Hi, this is Mr. Yeager. I'm looking at springs one more time, and I'm trying to show you how energy with spring situations will be graphed. All right, and we basically have two different types of graphs, and then one last situation I just want to quickly show you. So what we're looking at here is basically a block is oscillating back and forth from an equilibrium point, which I'm just going to label here. This would be x equals 0. This would be negative x, and this would be positive x. This would be the maximum amplitude that it reaches while it's oscillating back and forth. What we're looking at is a block spring system. Okay, that means that we can include potential energy involved with it. If I'm only looking at the block, I can only involve kinetic energy. And this is completely frictionless. Okay, so how do I approach a problem where it says let's first look at just the kinetic energy. What would the kinetic energy graph look like when an object is oscillating back and forth between negative x and x, positive x? What I like to do is I like to label 3 points first for basically all of these, except for the mechanical energy. For the kinetic energy and the elastic potential energy, I want you to figure out where is it minimum kinetic energy and where is it maximum kinetic energy. So if I'm talking about kinetic energy, I'm talking about where is it not moving versus where is it moving, and where is it moving fastest. So if I think about it, if I start at negative x over here, that's where I pushed it all the way back, and it's pushed, it's moving, and it stops. So at negative x, it's not moving, which means it has 0 kinetic energy. So we start down at the bottom there. Then what's it going to do? It's going to speed up, speed up, speed up, speed up. All right, what's happening at x equals 0? I'll talk about it in a minute. Right after x equals 0, that means now I've stretched it too far. It's getting stretched too far. So it's immediately slowing down after x equals 0 until right here, it's v equals 0 again. So it's v equals 0 on both sides, which means the kinetic energy is 0 on both sides. In the middle is where we're going to have the maximum speed, because it's going to keep on accelerating all the way to that point. It has a force all the way to that particular point. So I can mark that at the top. Again, if they have to have a specific number that you calculate it, but otherwise, they usually just say which graph will show is best representative. So those are our 3 points. So the next thing is, basically, should I pick the graph where it's a straight line at each other, okay? Or should I pick the graph where it's probably going to show you a curve, okay? So which one is it going to be? So what you need to do now is obviously go, what's the relationship between KE and X? KE and X. What is the relationship between the two? All right? And so what we can look at here is we go, okay, what is the relationship between KE and X? Well, if it's frictionless, that means kinetic energy is equal to elastic potential energy. In other words, the change in kinetic energy is equal to the change in elastic. As one goes up, the other one's going down. It's just like gravitational energy when an object's falling. Gravitational decreases as kinetic increases. And since there's no friction, this is occurring perfectly. So I have these two things set equal to each other, because I don't, obviously K is just 1/2 mv squared. Nothing x shows up in that. But the thing is, if I know these are equal, I can say Ke equals 1/2 kx squared. What does that show you? It shows you that there's a square relationship between x and Ke, an exponential relationship, which means it's going to curve, okay? And that's basically your answer there. It's going to get higher and higher and higher, all right? But obviously this is going to decrease exponentially, and then it's going to increase exponentially, okay? Back down, not increase, but obviously it's curving because it's an exponential relationship, okay? So let's move to the elastic potential energy. This is going to be a lot faster. It's the opposite of the kinetic energy. As one is going up, the other one's going down. That means at x equals 0, there is no elastic potential energy. There is no elastic potential energy there. At the maxes, there's a lot. It's perfect. It's completely stretched out. All right? And then it's basically the opposite curves. It's going to be a U. Okay? The opposite curves as it goes out. All right? It's going to decrease exponentially and then increase exponentially. All right? What about the mechanical? Well, that's easy. Is the mechanical energy changing? Mechanical is elastic plus kinetic. Is the total amount changing at all? No. So that would be perfectly straight. Okay? Perfectly straight. So these are 3 classic examples when you're involving kinetic energy and distance. The next one that they like to do, same situation, x equals 0. It stretches from negative x to positive x. But instead of looking at distance, we look at time. All right? And this one might be a little tougher because you're going, okay, once again, is it going to be a straight line or is it going to be curves? Okay? And so there's two ways to look at this. One, think about what a wave looks like. This is creating a wave. If I held a piece of paper under this and this was a pen, what type of shape are you going to see as you pull it back and forth? It's going to be a curve. But how do we specifically justify that? We could just say that it's accelerating. The object is accelerating the whole time. How do I know that? Because there's a force applied. And what's that acceleration doing? It's constantly changing. All right? So this is definitely going to be curved. All right? We could also just go, hey, kinetic energy is 1/2 mv squared, and obviously the velocity is squared. If I put that with t, it still has this square relationship going on. So now the only thing is, you know, where are we starting? If I start at negative x, I already said it's starting at 0. So what we're going to see here is it should basically curve up and curve down, curve up and curve down. That's why we call this, again, simple harmonic motion, because it creates that wave pattern. The elastic potential energy in this case is just going to be the opposite. It's going to start up high and go down and up and down. Basically, if I have these on top of each other, wherever this is on the bottom, kinetic energy should be on the top. What's the mechanical energy going to do? Boring, straight line. Okay? So that's what you're looking for in these particular graphs. We're basically going to make these wave graphs, okay? Or some people call them sine graphs. All right? So that's what we can basically see with these particular situations. Okay? So the last thing I want to quickly mention, all right, because this could always come up, is the formula for EPE is 1/2 kx squared. And sometimes they're going, okay, where did this formula come from? Where did this formula come from? Use a graph to illustrate where this comes from. And you're going to go, what? Use a force distance graph. All right? Well, if we think about a force distance graph for a spring, force of a spring is k times x. If it's force versus x, as I can see here, y equals mx, it should just be a straight linear line with the slope equaling k. All right, equaling the spring constant. Now the thing is, what if I take the area underneath this particular line? All right, because it is force and distance, isn't it? Force distance, what do we remember that about? Force times distance is equal to work. If I find the area under this line, it's equal to work. And what does work equal? Work equals a change in energy. Well, how is this going to equal a change in, specifically, elastic potential energy? Well, let's think about this. All right? If I find this area underneath this line, and it's always going to be a nice slope line. It's not going to be a flat line. It's going to be a straight slope line. How would I find the area of this line? It would be 1/2 times the force times x. So 1/2 F times x. The thing is, what does F equal? F equals k times x. Sorry, I'm going to come up here. So if I plug this in, I get the area, which equals work, equals 1/2 kx times x. What does that equal? 1/2 kx squared. Yay! That equals elastic potential energy. Okay? And so that's, again, where that formula is derived, or can be derived from, where this is basically equal to the work done by the spring. The work done by the spring is its elastic potential energy, which is 1/2 kx squared. All right, thank you.